Hello everyone, today we'll discuss chapter 12. The topic is engine heat transfer. This is the topic that will be discussed in this chapter. The first subtopic is modes of heat transfer. So we will review a bit different modes of heat transfer. So heat conduction and then convection and radiation. The next one is heat transfer and engine energy balance. The last subtopic is the effect of engine variables on the engine heat transfer. Heat transfer is a parasitic process that removes a significant fraction of the fuel chemical energy. It is an inherent loss in an internal combustion engine, so we cannot remove this heat transfer completely. We can reduce it by a certain device or having a new design of the engine. This heat transfer affects the engine performance, efficiency, and emissions. It lowers the average combustion gas temperature and pressure, and thus lower the engine indicated power. So it has a direct impact to the engine conversion efficiency. It affects the onset of knock. So as you learn in chapter 10, knock is strongly controlled by the unburned gas temperature, and this unburned gas temperature is strongly impacted by the wall heat transfer. It impacts the emission formation process. In the previous chapter, we learned several NOx, soot, HCCO formation processes. For example, soot. The soot production is controlled by the soot formation and soot oxidation. And the soot oxidation is strongly controlled by the combustion temperature. And the combustion temperature is strongly impacted by the wall heat transfer. This heat transfer also governs the power that can be obtained from exhaust energy. Minimizing the wall heat transfer in the chamber will increase the exhaust energy, which will increase the extraction of this exhaust energy by, for example, a turbocharger. This wall heat transfer is a periodic, so it means we will have a high wall heat transfer during the combustion process, and then modest heat transfer during maybe the end of the exhaust stroke or early intake stroke, and then there might be a heat transfer from the mixture to the gas during the combustion process, and in the other time there will be a reverse direction of this heat transfer, so from the wall to the mixture, especially during the intake stroke. So this wall heat transfer or this heat flux varies substantially with the time as well as with the location. This picture is showing an example of an energy balance in the diesel combustion engine. So we have three different data here depending on the number of injector hole. So we have 8 hole, 12 hole, and 16 hole. The first data here is the chemical energy. So this is the energy contained inside the fuel. So you know that the combustion efficiency in the diesel engine is close to 100%. So you can assume that this chemical energy is the fuel energy. And then the next one here is the gross indicated work. So this is indicated power. So this is the energy that is transferred in the piston. And the next one here is the energy loss due to wall heat transfer. So this is the in-cylinder wall heat transfer. This is the heat transfer through the piston top surface, cylinder liner, and cylinder head, and the valve. And then the last one here is the exhaust gas energy. Minimizing this wall heat transfer will either increases the exhaust energy that is good for a turbocharger. It can also give some increase of the indicated power which give a direct impact to the engine thermal efficiency. So from this feature you can see that how important is the technology that can be designed to reduce the wall heat transfer, as it will have a direct impact to the engine performance. The next one is modes of heat transfer. There are several different modes of heat transfer that occurs inside an internal combustion engine. The first one is conduction. So in this conduction, heat is transferred by molecular motion, and this molecular motion is driven by a temperature gradient. This conduction heat transfer occurs within the solid as well as within the fluid. So it also occurs within the fluid, but it is much less popular than the one that occurs within the solid, because the heat conduction within the fluid is much smaller. To quantify this conduction heat transfer is follow a Fourier heat conduction formula. So this is equation 12.1. Q dot, so this is flux of heat, equals to K, thermal conductivity of the medium, times temperature gradient. So this one, delta T. For a steady 1D temperature variation, we can formulate this equation 12.1 into this equation. So Q dot equals to Q, a capital letter, so this is heat transfer, over A, so this is the surface area through which this conduction heat transfer occurs, equals to minus K times dt over dx. We have a minus sign here because the temperature gradient, so this one is dt over dx. So this is calculated by subtracting the downstream temperature by the upstream temperature, and the upstream temperature is always higher than the downstream temperature. Therefore dt over dx here is a negative, so to have a positive Q dot, so we need to put a negative sign in front of this equation. This conduction heat transfer occurs mainly within the solid of the engine, so the solid zone of the engine. So we have piston, and then cylinder head, engine block, and so on. As I mentioned to you, it also occurs within the fluid. So we have a gaseous within the in-cylinder chamber, and then we have a liquid region inside the coolant passage. The next one is convection. So in this convection heat transfer mode, the heat is transferred through two mechanisms. So this mode of heat transfer comprises of two mechanisms. The first one is the energy transfer by the bulk macroscopic fluid motion, and the second one is by the molecular interaction or molecular motion. And the second one here is actually the conduction heat transfer. So this convection heat transfer occurs between a fluid and a solid, as well as within the fluid. And the heat transfer evaluation follow the Newton cooling formula, equation 12.2. Q dot equals to Hc, so this is the convection coefficient, times the temperature of the fluid minus the temperature of the wall. So in here you can reverse the position between T and TW depending on which one is higher, so that you can always get a positive value for the convection heat transfer. The convection coefficient Hc in equation 12.2 is calculated with the following correlation. So it's equation 12.3. So this Hc is a function of the viscosity of the fluid, and then velocity for sure, and then density, Cp, K, thermal conductivity. And we have a couple constants here, m and n. So m and n here are typically 0.8 and 0.3. And then in case nucleate boiling occurs inside the engine, for example, inside the coolant region, then this Hc is increased, and we should use a different relationship for this Hc that is estimated, or this is built for nucleate boiling condition. The next one is radiation heat transfer. So this heat transfer occurs through the emission and absorption of electromagnetic waves. It occurs from the high temperature combustion gases and the flame regions to the combustion chamber walls. And this heat transfer by radiation occurs from all the hot external surfaces of the engine. This radiation heat transfer is only significant in diesel combustion due to twofold. The first one is that the combustion temperature in the diesel engine is usually higher than the one in spark ignition engine due to a higher compression ratio. The second one is the contribution of the soot that is produced inside the diesel engine to this radiation heat transfer. So because of this soot, we have a significant radiation heat transfer inside the diesel engine. To estimate this radiation heat transfer, it's follow equation 12.4. So Q dot equals to sigma times T1 to the power of 4 minus T2 to the power of 4. And sigma here is the Stefan-Boltzmann constant. It's equal to 5.67 times 10 to the power of minus 8 watt over square meter over K to the power of 4. This picture is showing a schematic of the overall heat transfer process inside an internal combustion engine. On the left side of this blue wall, so we have a gaseous zone, so you can assume this one is a gaseous inside the cylinder chamber, and then this wall is the cylinder wall or cylinder head wall. You can also assume that this one is the piston wall. Okay, this one. And then to the right of this wall is the coolant region. So in the gaseous region on the left side of the wall, we have convection heat transfer and radiation that transfer energy from the gaseous region to the wall. So in here it is represented by Q dot CV and Q dot R. So this is convection heat transfer and radiation heat transfer. And then inside the wall, within the wall, we have conduction heat transfer. So this is a Q dot CN. And then to the right of the wall, we have energy transfer by convection from the wall to the coolant. Okay, so we'll talk about this coolant in the next chapter. So in the gas side, we have equation 12.5. So the heat transfer is the sum of the convection heat transfer and radiation heat transfer. So this is the convection heat transfer formula, and this one is the radiation heat transfer formula. We have epsilon here to represent the emissivity. So I think you learn these properties in heat transfer class. So if it is a perfect black body, you have emissivity of 1, but usually the actual body is not a perfect black body. So in the engine, you will have emissivity less than 1. And then within the wall, we follow equation 12.6. So Q dot Cn, so this is conduction, equals to K. K here is the thermal conductivity of the cylinder or cylinder head or piston, times T wall in the gas side minus T wall in the coolant side. So TWG minus TWC over TW. So TW here is the thickness of the wall. And then in the coolant side, it's follow equation 12.7. So this is the convection heat transfer equals to It's Cc, so this is the convection heat transfer in the coolant sides, times TWC, so this is the wall temperature of the cylinder or the cylinder head or the piston in the coolant side, minus the Tc with the upper bar, so this is the average temperature of the coolant. And then from what you have learned in heat transfer class, you can also formulate this heat transfer in terms of the thermal resistance. So you have a thermal resistance in the gaseous side due to the convection and radiation. And then you have the thermal resistance due to heat conduction within the solid region. And this one is the thermal resistance due to the convection heat transfer. And this is in the coolant side. And then you know this configuration is a serial configuration, so you can have the total resistance here is the sum of the resistance in the gaseous side, resistance within the solid region, and then this is the convection in the coolant side, equation 12.9. The next one is heat transfer and engine energy balance. Let's start by drawing a simple schematic for the thermodynamic system of the engines. So let's say this is the engine block, and then I have a piston. Then we have a conrod here. And then this blue dashed line represents the system boundary. Okay, now we apply one by one the energy to and from this thermodynamic system. So we have energy coming into the system from the fuel supply. So let's say this is EF, so this is the fuel energy inputted to the system. And then this engine is doing a work. So in this case is transferred to this conrod. So we have a PB here. So this is the engine output power. So the engine brake power. And then there'll be an energy transfer to the surrounding. So this is in terms of the cooling from the coolant. Okay? So the coolant needs to be cool to maintain its temperature lower. So we have, let's say this is Q cool. So this is the energy transfer from the engine to the system to coolant cooling. And then there will be an energy transfer to the surrounding. So this is due to the convection and radiation at the outer surface of the engine, as well as the cooling of the oil. So in case the oil is cooled separately from the coolant cooling. So let's type this one as the Q miscellaneous. So we have convection, radiation at the outer surface of the engine, and then the oil cooling as well. And then some of the fuel, small amount of the fuel, might not be burned during the combustion process, and it exits the engine along with the exhaust gas. So can type here is the QIC because of the incomplete combustion. And then the next one here is the energy exiting this engine system that is contained within the exhaust gas. So can type here is the E exhaust. Okay, the energy balance formula for this engine system follows this equation 12.11. On the right side we have the inputted fuel energy, and this is balanced by the brake power from the engine, and this one is the coolant heat transfer, and then this is the miscellaneous heat transfer. So convection, radiation at the outer surface of the engine, might be also the oil cooling. And this one is the energy exiting the system. due to the incomplete combustion, so few amount of the fuel exit the engine along with the exhaust gas. And this one is the energy exiting the engine within the exhaust gas. This table is showing a typical range of each energy here. The first one here is for the spark ignition engine, second one is for diesel. So spark ignition engine here has a pp within 25 to 30, so it might be in the lower side here because we have been able to have a spark ignition engine with a new technology with the PTE around 38, 39, even 40%. And this one is the heat transfer due to the coolant, and this one is convection radiation as well as the oil cooling. This 6 to 15%, this is coming from the incomplete combustion, so it's high for spark ignition engine. And the last one here is the energy within the exhaust gas. Next one is for diesel. Diesel usually have a better PTE, therefore it has a higher PP than spark ignition engine, so 35 to 40%. So it's also on the lower side. So right now we can have even close to 48% PTE for the diesel engine. And this one is for the coolant, and this one is miscellaneous. And then diesel has much higher combustion efficiency, therefore it has much lower energy due to this incomplete combustion compared to the spark ignition engine. And this last one is the energy within the exhaust gas. This one is another representation of engine energy balance in terms of what it's called energy flow. So in my opinion, it is better than represented in a table. So starting from the left side, so we have fuel energy here. So this is the fuel energy that is inputted to the engine. Some of this fuel energy will be transferred into the indicated work, so PI or indicated power, and then PI minus friction work, so PTF, so this one, it will be a PP, so this is the engine brake power that is available, let's say, at the entrance to the dyno, so that can be measured by the dynamometer. And then we have a PTF, this is the friction power. Some of this friction power will be transferred to the coolant, and then a few amount will see here go to the miscellaneous, so it will be cooled by the oil. And then this one is the energy within the exhaust, which is the sum of the energy due to the incomplete combustion. So this is the region with the dot here. So this one, this is the HIC, so this is the energy inside the exhaust gas energy, and this is due to the incomplete combustion. And this portion is the sensible energy within the exhaust gas. Okay, and then we have a Q dot wall here. This is the energy in terms of the wall heat transfer. And then what will be cooled by a coolant here is this Q cool. This is the sum of Q dot wall, and then sum of this friction power, so PPF here coming from this one. And then also this Q dot CE here is the heat transfer in the exhaust port, exhaust manifold, and so on. And this one will be the exhaust energy downstream of the exhaust manifold. And once again, this one is due to the incomplete combustion, and this one is the heat transfer at the outer surface of the engine, plus might be the oil cooling. This picture is showing an energy balance for a gasoline spark ignition engine. and it is a function of engine load, so in terms of BMEP in kilopascal. And then the engine operating condition is at 2000 RPM, and the load here is vary from, let's say, this around 100 kilopascal to around 900 something kilopascal. As you can see in here, PP has a maximum one around this number. Okay, so high engine load has a better brake thermal efficiency, represented by higher PP here. It is in percent. Okay, and then the next one here is the heat transfer to the coolant. Okay, and then this one is the heat transfer to the oil, and this one is the sensible exhaust gas energy, and this one is due to the incomplete combustion, and then the next one here is convection and radiation, I think, to the surrounding. The next one is heat transfer measurement. The surface temperature can be measured by a thermocouple. The feature on the left side here is showing an example of the surface temperature measured in the cylinder head, and on the right side is the estimated heat flux calculated from the surface temperature. So you can see in here that surface temperature is high, especially during the combustion process. However, this surface temperature change is much smaller than the change in the gaseous side. So this one only change from around 380 to 388 Kelvin. While in the gaseous side, we have the temperature change, let's say, from 400 Kelvin during the intake stroke to the 2000 Kelvin during the combustion process. So this tells us that the penetration depth of this transient gaseous temperature is much smaller. And then the feature on the right side is the surface heat flux. So this is in terms of the unit is megawatt per square meter. So it has the highest heat flux during the combustion process, and this is mainly due to the high temperature difference between the surface and the gaseous temperature. Next topic, or which is the last topic, is the effect of engines variables. The following variables affect the engine heat transfer. So we have engine speed, engine load, overall ignition ratio, compression ratio, spark or injection timing, and then throw and squeeze motion, mixture inlet temperature, coolant temperature, composition, wall material, as well as the wall deposit. Of these variables, speed and loads have the greatest effect. This is an example of the convection coefficient empirical correlation. So it's a function of a constant, and then B here is characteristic length, which is usually the engine bore. P here is the engine cylinder pressure, which is mainly controlled by the engine load. Temperature, this is also mainly controlled by the engine load. W here is the gas velocity, and it is mainly controlled by the mean piston speed, which is the engine speed. And you can see in here that this heat transfer coefficient governs the amount of the wall heat transfer. This feature is showing the effect of engine load with the wall heat transfer, and the wall heat transfer here is represented with a different crank angle in the horizontal axis. The engine load here is represented by different volumetric efficiency. So lower volumetric efficiency here represent, let's say, mid load, and then this 0.8 and 0.9 is a high load. As you can see in here, higher engine load increases the wall heat flux, and this is estimation in the natural aspirated spark ignition engine, and this analysis was conducted at 1000 rpm. And this picture is showing the effect of spark advance to the wall heat flux. Again, it is plotted a function of crank angle, and the engine is a naturally aspirated spark ignition engine at 1000 rpm and mid load. As the spark is advanced, the wall heat flux increases. So this is because of the increased combustion pressure and temperature. And this feature is showing the effect of engine speed. So we have a 500 rpm, 1500 rpm, and 2500 rpm. As the engine speed is increased, so the wall heat flux increases as well. And it's the same engine type, so naturally aspirated spark ignition engine, and it is at mid-load operating condition. This feature is showing predicted average heat transfer rate. It is represented as a percent of the fuel energy, so in percent of the fuel energy for a different engine load. So A is 163 kilopascal, B is 325, and C is 655 kilopascal. And the engine here is an 8-cylinder with the total volume of 5.7 cubic decimeter or 5.7 liter. So this spark ignition engine, and this is a function of engine load, so 3 engine load, and this one is engine speed. As you can see in this feature, that the percentage of heat transfer loss decreases with the increase of engine speed and the increase of the engine load. So this is showing the lowest percentage of the heat transfer, and this occurs at the highest engine load, for this case C here, and the highest engine speed 3000 rpm. This is showing the predicted average heat transfer rate in fuel energy, so percent of fuel energy, as a function of equivalent ratio phi, and this one is the combustion duration. Okay, so CA90 minus CA10. As you can see on this figure, equivalent ratio has a strong impact to the heat transfer percentage. It has the highest one around phi of 1 here because of the highest combustion temperature. And then the burn duration has a modest impact to the heat transfer here. The longer burn duration has a lower heat transfer percentage because of a lower combustion temperature. This feature, I think, is similar to the previous slides, but the combined engine variable here is a spark timing and then the combustion duration. So advancing spark timing, so it's mean we go to the right here, increases the heat transfer percentage, and then having a longer combustion duration decreases the heat transfer percentage because of lower combustion temperature. Last topic is coolant composition. Automotive liquid coolants are a mixture of ethylene glycol or propylene glycol with water, usually in about equal mass proportion. So we have 50% of water and 50% of glycol. We need to add this glycol as an antifreeze. We know that water will freeze at 0 degrees C, and we don't have to have this coolant freezing during the winter season. If you don't have the freezing problem during the winter season, we do not need to add glycol because the cooling performance of water is better than the one for glycol. This table is showing the ice flaking and boiling point temperature for water glycol mixture with a different amount of glycol percentage. As we increase the glycol percentage, the ice flaking point temperature decreases. So if you have 10% glycol, the ice flicking point change from 0 to -4, and then with 50% glycol we have ice flicking point temperature of -39 degrees C. And then in the other side, the boiling point increases with the increase of the glycol. Okay, we have completed this chapter 12 discussion. Thank you and stay safe.